Hello, my name is Ernest Tay Mate, and I am the coordinator of the African Space Station project and also one of the coordinators for this competition. I am also one of the engineers who designed and launched Ghana's first satellite into space in 2017. You are welcome to this competition. It's the first of its kind, and I would like to say congratulations for being a part of it. This is the tutorial video, and in this video, you are going to be taken through a series of lessons, and the lessons here are going to guide you on how to be able to answer the questions and to be able to produce results for the practical work that you'll be given. I'm going to have my students of All Nations University, to take you through certain particular topics, and I believe that you are going to learn a lot. You are going to be taught basics of satellite technology. You are going to be taught about space science, rockets, and how to analyze satellite signals. And so please consider this approach very practical for you, and I would like to encourage you to do it by yourself. As a group, I would like to encourage you that you should allow each and every single student in the group to have their hands on the work. Here at All Nations University, our lessons and our tutelage is purely practical. It's practical, and it's because we have the tools and the equipment here to equip every engineering student. I'll be glad if one day you join All Nations University and I will lecture you in some courses. And so just relax, go through the video, and I know that is going to be a great learning process for you. Thank you very much.
Hello everyone, I am Dunamis Uzochukwu, an Electronics and Communications Engineering student at All Nations University. Here we are going to learn about the basics of satellite communication. We will discuss how satellites and satellite communication work, its benefits, and I'll introduce you to the concept of noise. So now, what is a satellite? The word satellite is actually a Latin word which means a smaller body revolving around a bigger body. As you can see in the illustration, there is a small orange ball moving around a big blue ball. The smaller orange ball is the satellite, and the big blue ball is the primary. So there are two types of satellites: natural satellites and artificial satellites. As shown here, the moon goes around the earth, making it a natural satellite, and then the earth itself goes around the sun, making the earth also a natural satellite. So now we're going to talk about artificial satellites and why artificial satellites. We are going to use illustrations for easy understanding. Now check out this photographer. He wants to take a photo of these 5 people. When he does so, most likely we will see just the first lady and the head of the taller guy that is behind her. So now, how is he going to take a picture of all 5 of them? He has to climb something to get a greater height and the better angle. When he takes the picture from here, most likely we're going to see all 5 of them in the photo. Also, look at this cameraman that has gone to one of the tallest buildings in his city. When he takes this photo, we are going to see a wide coverage of the city, and if he goes to a mountain, the coverage will be even wider. So by increasing your height, you are increasing your coverage. So now, where is space? You heard a lot of people talking about space, this very far place up there. So it has been agreed that space starts from an altitude of 200 kilometers above sea level. So now you may not really understand how high that is. So let me give you an idea of what that looks like. Look at this illustration on the screen right now. If you're able to jump up to just 3 kilometers, we may not be able to see you again because you will be lost in the clouds already. And airplanes fly between 10 and 15 kilometers high. But space objects are 200 kilometers above sea level. So if you begin to enter into an altitude of 200 kilometers and above, you are considered a space object. And this is how you'll be seeing the Earth. And so if you were the photographer, you will take a very wide picture of the city. Once you have entered space altitude, the laws that govern space will apply to you. By the way, altitude is different from height. So altitude is height measured from sea level. So you hear 200 kilometers above sea level. So that's altitude. So now we're going to talk about the benefits of satellites. The major one and the main thing is remote sensing. Remote sensing. So remote means that you're at a distance, like using a TV remote. At home, you just sit on the couch and you press the remote and the channel changes. While sensing means to gather data. So remote sensing means that you are gathering data at a distance. This image here shows a tsunami at sea. And as we are on land, we have no way of knowing what destruction is about to fall upon us. But a satellite can see this and warn us beforehand, enabling us to have safety measures. So now we're going to talk about the benefit of satellites for communication. Look at this illustration now. This lady here is speaking and is trying to talk to her friend that is over here. But there's a mountain between both of them. So when she speaks, her friend won't hear. So to solve this problem, they devised a means which involves these two guys on the mountain. So now the first lady will speak, this guy will hear, tell this guy, and then this guy will send the message or tell the second lady. So now in this illustration, these two guys are representing what the satellite does. So one major benefit of satellite communication is global communication. Satellites can be used for global communication. Through a satellite, you are able to make a call from one country to another, overcoming whatever obstacles. Satellites are also used for broadcasting, like your satellite television, for example DSTV or GoTV, where you watch sports or other form of cable entertainment. Then we have navigation, for example Google Maps, and then meteorology, which is the study of the atmosphere and is used for weather forecasts. So where are artificial satellites? This topic was included because when we launched our satellite in 2017, people were asking where our satellite went, whether I went to the moon or I went to Mars, which is what I want to explain to you now. Now you can see this illustration here of our solar system, and note that the planets here are not drawn to scale. By the way, here are two fun facts about our solar system. 1 million Earths can actually fit into the sun, and if you are to take a trip from Earth to Mars in a commercial airplane, it will take you about 6.9 years to get to Mars. And here's another interesting thing. Do you know that you can't walk on Jupiter or Saturn because they are gas planets? Okay, now back to the illustration. This big dark dot here is the moon, which is orbiting the Earth. And the distance from the Earth to the moon is actually a very great distance. And the value of that distance is 384,400 kilometers. Just imagine that. So now in this illustration, the orbits of artificial satellites are actually just within this light green outline here. We have talked about where artificial satellites are. Now, how do we get our artificial satellites to space? I believe you know about gravity, where whatever you throw up comes back down. So how do we overcome this? It is done by using a rocket. A rocket is a vehicle that uses jet propulsion to accelerate without using any surrounding air. And it is currently the most reliable way to take our satellite to space. Now, people wonder why all rockets have similar shapes. This is because rockets have what is called a streamline shape, which gives it an advantage. The streamline shape is found in fishes and birds. So now, a streamline shape is a shape that reduces friction or drag between a fluid, such as air or water, and an object moving through it. So now that we understand rockets, let's look at illustration A. On this rocket, there's upward force and downward force. When these two forces act on a body and they are comparable, you have the resultant force in this direction. So now look at illustration B. We have Earth's gravitational pull as the downward force and the propulsion of the rocket as the upward force. So the rocket's propulsion is enough to escape Earth's gravity to get to space, and the rocket is carrying the satellites. So now, when the rocket gets to space, the satellites will detach or be deployed, and it will move in the direction of the resultant force. And this circular path that the satellite is moving in is known as the orbit. So take note that the satellite moves in its orbit without any man-made propulsion systems. It naturally moves with the benefit of the resultant force. So now that our satellite is in space, there are three types of satellite orbits according to their altitude, as illustrated here. So note that these lines are just for illustration. There are no visible lines in space. So starting off, we have the lowest orbit, which is known as the low Earth orbit. It is indicated here by the green part, and satellites in the low Earth orbit are closest to the Earth, with an altitude range of 200 to 2000 kilometers above sea level. And most of the university and scientific satellites are found in this low Earth orbit. Also, satellites in the low Earth orbit are the fastest satellites. As you can see in the illustration, the satellite in the low Earth orbit is revolving faster than the others. By the way, revolving is different from rotating. Now that our satellite is in space, we need a way to receive from it, and this is made possible by what is known as a ground station. Whatever information the satellite receives in space, it has to send it to us for our benefit. So we need ground stations that are able to receive the satellite signals effectively. For example, this ship needs navigation data for ocean travel. It will need to receive signals from a GPS satellite, so it will have a ground station. Students can also be a ground station. For example, here is students in All Nations University receiving important data from a satellite. So we have the space stations or the satellites, and then different kinds of ground stations. Okay, so now that we know what ground stations are, we are going to talk about how the satellite communicates with the ground station. So, satellite communication is a form of line of sight communication where the satellite has to be in the ground station's field of view in order for the ground station to receive signals. So now let's see how a field of view works. So field of view refers to the extent of the observable world that can be seen at any given moment through an instrument, such as your eye, a camera, or a microscope. It is usually an angular measurement. So now, in this case, the FOV, or the field of view, defines the range within which the ground station can maintain a line of sight connection with the satellite. In this illustration, the field of view is indicated by these hash triangles. So as the satellite revolves, it moves towards the receiver, and where it enters into the receiver's field of view is referred to as the acquisition of signal, and where it exits the field of view is referred to as loss of signal. The satellite also has its field of view, which is illustrated as this green triangle. The field of view determines the coverage of the satellite on the Earth. Now, as seen in illustration B, the coverage of the satellite on the Earth is known as the satellite footprint. So, it is only antennas that are in the satellite footprint that can receive signals from the satellite. So, as shown in this illustration, the owner of this antenna has tilted it in a way that the field of view of the antenna is facing the field of view of the satellite. So because of this, he's going to receive a very strong signal. So now let's say he has tilted it in the wrong direction. There will be no signal because the two FOVs are not intersecting with each other. And now in this scenario, it is tilted at an angle where only a small part of the antenna's field of view is intersecting with the satellite's field of view, causing him to receive a weak signal. Let's say like out of 100% signal strength, he will get only like 25%. So in this computation, we are communicating with satellites that are from the low Earth orbits, which, as I said earlier, move very fast. So a satellite in the low Earth orbit takes about 5 to 10 minutes to pass over your country, and the satellites in these orbits move with an average speed of 7.8 kilometers per second or 28,080 kilometers per hour. Now, you may not understand how fast that is, so I'll bring something to your knowledge that you might be familiar with. So, this is a man shooting a gun. The satellite in the low Earth orbit is actually faster than the bullets that is shot from a standard handgun. Okay, now that we've talked about how satellite communication works, let me introduce you to a major issue in satellite communication. It is known as noise. Noise is a serious issue that really affects the quality of satellite communication. So now, what is noise and what is its impact on satellite communication? So now let me give you the definition. Noise is any unwanted signal that interferes with the desired signal in a communication system. The impact of noise can degrade the quality of communication, reduce data rates, and increase error rates. Now, this is the sample of a normal message.
Good day, thank you for joining us.
And this is the noisy version.
Good day, thank you for joining us.
So, When we talk about noise, we also have to talk about signal loss. Signal loss refers to the weakening of a signal that is transmitted across a distance. Now, look at these images. We have image A, it's clear, you can see that it's a clear image of a tsunami. Then image B, where some power has been lost, it gets a bit blurry. Then at point C, it has become so blurry that you cannot really tell what it is. So now we're going to talk about the sources of loss. Now, the major source of signal loss is known as the free space path loss. So this refers to the loss of signal strength as it moves through free space. This is because the signal spreads out over a large area as it travels farther away from the source. So when a signal is transmitted from a satellite to a ground station through free space over a certain distance, like from the altitude of the satellite to the altitude of the ground station, it loses power. Now take a look at this illustration here. In this scenario, the satellite is transmitting at a power of 80 watts, and because of free space path loss, as you can see illustrated here, the ground station is receiving about only 20 watts. So now the power that will be received by a ground station after the signal experiences the free space loss can be calculated using the Freeze formula. So now in the Freeze formula, it shows us that the power received is dependent on the power at which the signal was transmitted, the gain of the transmitting antenna, which is how good that antenna is, and the gain of the receiving antenna, which refers to how good the receiving antenna is. In this case, the transmitting antenna is the satellite's antenna, and the receiving antenna is the ground station's antenna. It's also dependent on the speed of light, which is 2.998 times 10 raised to power 8 meters per second. And then it also depends on the distance between the transmitting antenna, that's the satellite antenna, and the ground station's antenna, and the frequency at which the signal was transmitted. So in this formula, the two major determinants of the power that is going to be received are the distance between the satellite antenna and ground station's antenna, and the frequency at which the signal is transmitted, and that is why they are squared over here. And because of this, a signal with lower frequency experiences less loss than a signal with higher frequency. So let's say in a case satellite transmits the first signal the same 80 watts but at, let's say, 150 hertz, which is a low frequency, the power lost will be smaller, meaning that the power received is higher than when that same signal is transmitted at a higher frequency, like let's say 1 kilohertz, to the same antenna over the same distance. And note that power loss makes a signal more susceptible to noise. Now let's talk about the sources of noise. First of all, we have system noise. System noise is caused by the activity of components in the electronic system of the satellite, such as the power supplies, processors, and other electronic components. And then we have thermal noise. The thermal agitation of electrons within the satellite's transmitter and the receiver's electronic components generates thermal noise. And also, another source of noise is the space environment. The space environment itself, including cosmic radiation and charged particles in space, can interact with satellite components, causing noise. So this is an example of what space noise might sound like. Next, we have the Earth's atmosphere. The Earth's atmosphere as illustrated here, contributes to noise through various mechanisms such as water vapor, oxygen absorption, atmospheric noise from lightning and other electrical discharges. So in a case where they are transmitting a signal where there's bad weather, like let's say and there's lightning storms and there's a lot of water in the air, water vapor, rain, it will cause noise in the signal that is being transmitted. Then also we have ground-based human activities. So man-made radio frequency interference comes from human activities such as broadcasting stations, your TV, mobile networks, that's your phone call companies, radar systems, how ships use to navigate, and the emissions from electronic devices. So let's say a signal is being sent from satellite to this antenna. This broadcasting station can broadcast a signal across here that can cause noise in this transmitted signal. And then there are also people in all these buildings making phone calls. So these factors can cause noise in the signal that is received. And then we have the relative speed of the satellite and the receiver. So the satellite's movement causes change in frequency due to what is known as the Doppler effect. So the Doppler effect in physics is defined as the increase or decrease in the frequency of sound, light, or other waves as the source and observer move towards or away from each other. So in this case, when the satellite moves towards the receiver, the frequency gets higher, and when the satellite moves away from the receiver, it gets lower depending on the orbit of the satellite. So that is all for the basics of satellite communication. Thank you.
Hello there. All right, my name is Bright Ayeno. I'm an electronics and communications engineering student here in All Nations University. So I'm here to show you or teach you how to go about signal processing, basically signal processing, and Morse code or CW decoding. So what is signal processing? Signal processing is transforming signals into useful data, extracting embedded information from such signals. So signals that you get from the satellite, those electromagnetic waves sent from the satellite and you've recorded, received from your receiver, it needs to undergo signal processing, and this is what I'm about to teach you. So extracting those embedded information, that data sent from the satellite, it needs to undergo signal processing. So I'm going to walk you through how to use Audacity, how to use CW decoder. At the end, you know what is expected from the processed data, what type of data you're supposed to have received, or what you're to expect, basically. So how to use Audacity? Well, it involves the amplification and filtering of signals, that's removing the noise in the signal and getting the clear, clean signal that you need for your decoding, for your interpretation or your decoding. First, for the signal processing, we'll use Audacity. Audacity is one of the softwares, and CW decoder. So the CW decoder will be used to decode the Morse code that's from the clean signal that you get. You get the Morse code, so you can interpret and get the information that you need, what you're expecting. So after hearing what it sounds like, you get that audio file, either in whatever format it is, you import it into Audacity. So that's what I'm going to show you. I'll walk you through how to go about this. So Audacity is a free software, easy to install, easy to use, used for signal frequencies at audio range, right? For any audio at all. So I'm going to show you how to work with Audacity, how to install it first, what you can do with it, and what you should use it for in this period of your competition and assessments. So first, let's move on to the installation. So the next video will be to how to install Audacity. So I'll show you after you've downloaded your Audacity file from a description or the link provided to you or the resources provided to you. You install it on your system, you save it on your system, install it, and then I'll just show you how to install it, right? All right, now onto how to install Audacity. So first, before you can install Audacity, you have to have it downloaded on your system. So I'm sure you should download it from the description on the YouTube channel, or you just download Audacity, the latest version. And now I have this file here. This is the setup software, and then you run it as administrator. Yeah. So right now, right click and then run as administrator. So you just follow the prompts. Next. Now I have Audacity already installed on my system, so I'll just go ahead with the installation just to show you how it is. So I'll click yes, and then install. So to take some few minutes, seconds, is very, very small. So now once it's done, it will be, you just have to launch Audacity. Okay, now you have Audacity installed, and this is the interface. This is how it looks like. This is how my Audacity looks like. It should be like this. Now you have on the toolbar, file, edit, select, view, transport tracks, generate, effects, analyze, tools, and help. So I'm going to walk you through how to use Audacity and what is useful. So now that you've installed Audacity, now you should know what you can do with Audacity. Okay, so first you can use Audacity to amplify signals. So to increase the intensity and volume or at which you can hear, that's the audibility of your audio signal or your audio file. Just to increase that volume, you can amplify using Audacity. The next is to trim, copy, cut, and paste. That's basically manipulating your audio signal, modifying it into the desired nature of what you need it to be. You can trim, that's reducing the length. You can copy a section of the audio to a particular part of the audio. You can cut it, and then you can paste it. That's two. And the third is analyze signals. You can use Audacity to analyze signal. When you want to get a visual representation of what your audio signal looks like, you can get it by analyzing signals. And the fourth is to filter. Filter, basically removing particular parts or particular frequencies of your signal and retaining a particular frequency. That's when you need to do something like that, you can use Audacity to filter your signals. And fifth, that's to remove noise, remove unwanted sounds that you definitely find in your satellite signals and audio files. You can use Audacity to do that. So I'll take you through how to do each and every one of these. So the first is amplify signals. So let's watch how to amplify a signal. Let's go to Audacity and then I'll show you how to do that. So now we're back on Audacity, and now you're to amplify a signal, a satellite signal. So first, before you can amplify, you need a signal. Yes. So right now you just have to organize your signals and where you can find it easily. So right now I have it on my desktop here. And it's open right now. So there are a bunch of signals here. You just pick the one you want to use. Right now this is it. So you can do a drag and drop to import the signal onto Audacity, or that's this, drag and drop, and it's imported. Or Ctrl-Z, you go to File, Import, go to Audio, and then you look for where you saved your audio files. I have it on my desktop, like I said, so I went to desktop, into the folder satellite signals, and I select the one I want to amplify. So now here is the signal for better view. Alright, so now to amplify it, you either have to want to select a particular part of the signal to amplify, or the entire signal. So in this case I want to amplify the entire signal, so I highlight everything. As you use your mouse and select everything, or you press Ctrl-A, it selects the entire thing. And after you do that, you go to Effect on the toolbar, navigate to Volume and Compression. Under that you have Amplify. It's as easy as that. So to give you a preset that you can use, if it's beyond a particular preset, you might know, but right now you can easily amplify it. To just apply, and then the signal is boosted and more audible than it was. And that's as easy as it gets. That's easily done in a way. So let's Ctrl Z, and then what if in a case where you want to just highlight, amplify a particular part of a signal, right? So you just select that part, same process, effect, volume and compression, amplify, then you press apply, and it amplifies that part, that section you selected. So it's as easy as that. So if you don't highlight it, it doesn't amplify. So be mindful of that. Second, trim, cut, and paste signals. It's very easy to do, and I'll show you right now. Okay, now the next step is how to trim, copy, cut, and paste, how to modify a signal, an audio signal. So first, let's open our Audacity right here. Right. So now we have to have the audio. Let's import it. Import the audio to amplify. Let's select this and open. So this is the audio we want to copy a particular section and paste it somewhere else. Maybe you want the beginning to be at the ending, you want the middle to be at the ending, or you want the ending, a particular part, the ending to be in the middle. You cut, copy, paste. Or you want to trim the signal itself. It's easy, you can use Audacity to do that. So let's try copy. So like this, you just highlight and you right click, and you have a bunch of options there. So you have cut, copy, paste, split clip, mute. Mute as in this part will not sound, or mute you want it to sound. So it's in the name. So right now we want to cut, so cut it, and it disappears. Now we want to put it at the back here, then we paste, and you have that. So now be mindful that you have to have a reason of cutting and pasting, or copying to paste, because you have to know the timestamp. You have to know the timestamp of the audio you're copying before you can cut to paste. You don't make any kind of mistakes. My apologies. So that's to copy the cut. Let's reverse, undo, and now what you want to copy, the same way, you just highlight and then Ctrl C, or right click, copy, then you come here, Ctrl V, or you paste, and then you can paste it here or wherever you want to paste it. Maybe you want to paste it here, but nope, there's not enough room. So if you want to paste in the middle, you have to split that track itself. So you split the clip, then you can move it a bit, then you can paste. Okay, before you can do that, you need to make enough room. So you're predicting about 3 seconds, so you make enough room so you can move the split track like this. You come here, you see this hand there, so it highlights the track you want to move, and you can drag it. Now you have enough room to paste the audio you copied, then you paste it. Easy as that. Then you can modify, arrange it properly, and it will be a complete audio set, right? An audio signal set. So it's easy as that. Alright, so now you know how to cut, copy, and paste, and the same technique, the same method applies to trimming. You can just highlight whatever you want to trim out and delete. You just, let's do that again. Highlight, select, and you just hit the delete or backspace key, and it's gone, right? Same thing here, delete. So I'm sure that was helpful. And third is to analyze signals. So to analyze signals, you have to understand something. First is understand the concept of a spectrum, right? And what can show a spectrum is a spectrogram. So a spectrogram is a visual representation of a signal's frequency spectrum over time. So you can use a spectrogram to show the strength or loudness or intensity of a signal at different frequencies and how energy levels change over time. So using a spectrogram, which you'll definitely see in Audacity, you can get a visual representation of a signal's frequency spectrum over time. So it's used in music, logistics, sonar, radar, speech processing, audio processing. So you just have to focus on the audio processing. So one thing you should note, the brighter the color, which you definitely see when analyzing a signal on Audacity, the brighter the color, it corresponds to the louder or the loudness of the sound. So the brighter colors correspond to louder sounds. So the brighter the color, the louder the sound. So moving on, let's just hop into Audacity and analyze the signal. Okay, so now on to the next step is to analyze a signal. So right now we're on Audacity again, and now you're given a task to analyze a certain signal. What do you want to analyze basically? So let's plot a signal, for example. Again, let's bring this nice satellite signal we've gotten. So we want to analyze it. What can we tell about the signal? What can we not tell? Right now we can see the signal is in a wave form. Yeah, once you zoom in, you can use your mouse to zoom, or you use this here to zoom. Let's zoom out. Okay, so right now we can tell that this signal is in the waveform in Audacity. So right now there are other ways you can look at it. Let's use a spectrogram to look at it. And now we can see something different here. Right? It's the same signal, mind you. It's the same signal. Let me right, and then just one sample of the signal. Okay, so now you have a spectrogram view of the signal you've gotten. You can increase the view like this, like so. Just use your mouse, come down here to get this arrow, bevel arrow, and then you drag down. So now you can see that this orange, whatever color this is, this particular part that is highlighted out of the black space is your signal. This is the frequency. If you see those numbers, is the frequency. So from 10 hertz to 19,000 hertz. But right now your signal is operating between 8,000 to 400. Now in the midst of this 400 to 8,000, there's white, there's noise, right? So where can you see the intensity of the signal? So observing through the spectrogram, you can tell that the signal is mainly at 700 hertz because most of the data and the intensity of the signal is in 700 hertz or within 700 hertz. Now if you want a more detailed view of this, you can also go to, you see a graphical representation of this right now. So to do that, you highlight the entire thing. That's, remember how to highlight. Control A, that's highlighting the signal. Then you go to analysis, right? Analysis or analyze, my apologies. Analyze or plus spectrum. And now this is a graph view of the signal here. Now you can see of the signal here. So this is a graphical view, as you can tell, and where you can find the peak of the signal is where your data will be and most information will be, and then you can trace it down and you can tell that it's at 700 hertz, right? That's basically how to analyze it. So you can tell that from here there is something being transmitted, most likely noise, but the main data in your signal, in satellite signal, will be at the peak the peak intensity of that signal. That's here at 700 hertz. So that's how you can analyze to pick out which particular frequency is. So with this analysis now, you can tell that, okay, at 700 hertz, I will get my information, I will get my data. Then you can use a filter to remove every other frequency and just retain the 700 hertz. And I'll show you that how to do that shortly. Now you've gotten that into understanding, you should also know how different frequencies sound, right? So when working with sounds, you have to understand this little aspect of it, that the louder the frequency, the more bass it sounds, right? The more bass it has, or the more bass you sound. So the lower the frequency, the more bass it sounds. The higher the frequency in this case, and the more the pitch you can get. So it's, well, I'll demonstrate with examples right now. Consider this two. Okay, so here you have two examples: an audio with frequency of 100 hertz and an audio with frequency of 1000 hertz. So one, you can see that one is lower and one is higher. Then it's just to know how it sounds. So I'm going to play each audio, so just to demonstrate. So for the one of 100 hertz, yeah. If you could notice with the lower frequency audio, it was very low that you couldn't hear so well because of the bass and the low intensity in it. So, well, if I play this 1000 hertz one now, you would hear it so well because of the pitch. Now let me just play it. So with this, you can tell and differentiate with how 1000 hertz frequency sounds and 100 hertz or any frequency within that range would sound. So moving on onto filters now, as the next thing that Audacity, you can use Audacity to do. So first, what does it mean to filter? Basically, it's just to attenuate the frequencies in an audio, but how to do that and in what manner. So there are different types of filters. So there are two types of filters. There are types of filters. One is the low pass and high pass filter. So a low pass filter is just that it allows low frequencies to go through while it cuts off high frequencies, and a high pass filter allows high frequencies and cuts off the lower frequencies. So when you're using that, a scenario like you have a frequency ranging from 8000 to 2000 hertz, right? 8000 hertz to 2000 hertz, but you want to keep all frequencies ranging from 8500 to 8000, right? So you want to cut off 1000 hertz to 2000, anything higher than that, use a low pass, right? But if you want to retain anything higher than 8500, all the frequencies higher than 1500 hertz, you use a high pass filter, right? So I'll just demonstrate that on Audacity, and you see how it is easy to use, right? Okay, now back to Audacity. Now I'll show you how to filter signals. So I've already given you an idea on what you can do with to filter signal. So when you need to filter a signal, maybe you have a frequency you want to keep in your particular signal. You have an idea of the frequency you want to keep. So you want to remove the remaining frequencies. So what you need to know is if the frequency is higher or lower than the one you have to remove, right? So the frequency you have to keep. If it's a higher frequency, you use a high pass filter. And if it's a lower frequency, you use a low pass filter. So basically what that does is that it allows the high frequencies you set at what frequency it should allow, and then it allows that to pass, it retains that, and then removes any low frequencies at all. and then for the low pass, it retains the low frequencies and removes any high frequency, any higher frequency from the preset. So now I'm going to show you. First, we have to import the audio signal. All right, file import audio. So you select the file or the audio you want to work on. Okay, now so this signal imported. Now to use the filter, you have to understand which where your signal is and what frequency it is before you can determine which type of filter you want to use. So to do that, you just need to analyze it by using the spectrogram, right? Uh, right now, this is the view. As you can see, uh, this is where our signal is more intense, between 2000 hertz to 1000 hertz, right? So we have to remove, we can clip off or cut off any other parts because it's most likely going to be noise. So to retain anything between 2000 to 1000, or if you want a better view, you can highlight, please first highlight, go to analyze, plot spectrum, and then you can tell that our signal here is more intense at 1000 hertz to, let's say, 2000 hertz, right? 2100 hertz. And beyond that, we don't need it. So we want to cut off anything below 1000 hertz. Anything below 1000 hertz. So let's go. While it's still selected, to use the filter, you go to Effect. And under Effect, you go to EQ and Filters. Now we want to keep the frequency is higher than 1000, so we use a high pass filter. So we click that, and then it's already selected here. So make sure you just confirm. Let's try 900 instead, right? So anything below 900 hertz will be cut off. Now this rule of here is just determining, picking the sensitivity or how much of the signal do you want to cut off. If the higher it is, the more intense it is, right? The lower, it might not do anything. So 6, it's not really advisable. So let's try 36 and apply. All right. So right now it's removed a high percentage of it, right? Because how sound is, definitely some will still pass. But right now, we focus on this color right here, this region, and you can tell that 900 is more intense. So if you want a clearer view, again, highlight, go to analyze, plot spectrum, and then you can tell that from 900 here, it drastically goes down, meaning you won't even hear it, right? So this is what your signal will retain. So we can still use this. And now let's try for the low pass, for the yes, the low pass filter, because you want to retain everything between, let's say, let's go back. Let's say 2000, 2100, right? Let's use 2100. So right now you highlight, you go to effect, EQ, that's equalizers and effects. But right now you're picking the low pass filter. So right now we're going to select 2100 hertz and intensity to, rule of intensity to 36 decibels. Now we'll apply. You can preview to listen to it, but right now it's just for demonstration. Let's apply that and see how it goes. Okay, so now it's been clipped off. Your data or signal is more intense in the frequency that you want, right? Let's go for a clearer view now. Analysis, plot spectrum. Okay, so now because of the filters, the signal that was almost here causing kind of worries is more clearer at the frequency, the designated frequencies it's at. So right now the peak will be at 1,545. 1,545. So you can work with that. So that's basically how to filter your signal, audio signals. It's as easy as it gets, it's as easy as you see. So remember, when you import the audio, it's definitely going to be in your waveform. You come to spectrogram and then you can see it, right? Okay. Now, onto the types of noise. Definitely, you come across different types of noise, or the common types of noise, which I will just give a brief explanation. Before you should know these different types before you can go into how to remove noise. So, one of the most common type of noise is the adaptive white Gaussian noise. So the white noise is a random sound or random signal. It's a sound that contains all frequencies at equal intensity. It is adaptive because it contains all frequencies, and it is Gaussian because it comes at equal intensity, right? So it's when you have an audio signal or a satellite signal, you're definitely going to get a white noise, and it's range at all frequencies of that signal. So with equal intensity, its uniform spectrum, its frequency spectrum is flat. So that's one way you can identify it. And one of the causes is natural sources. You can get it anywhere in free space when transmitting in free space. Ocean waves cause that, wind blowing through space, through trees, my apologies, and rain and free space itself. And then man-made sources like electronic devices. Whenever you're listening to your radio or watching TV, sometimes you get this shisha sound. I'll play the audio, an example of a white noise, so you understand what I mean. I'll just play that right now. So that's exactly how a white noise sounds like. I'm sure you're familiar with this sound, just the shishing sound. So there's a particular way to remove this noise because it's unwanted. It's not carrying any information. It's just going to be stuck in your audio signal or your satellite signal. So you have to know how to remove it to retain your data. Another type of noise is the thermal noise or the system noise. So thermal noise, system noise is common in system components, right? It's caused by overheating or temperature increase, resistance, or physical limitation. So it's randomly moving electrons in a conductor. So when you have, and in the sense of a satellite now, the transmitter sending it down to Earth, so a ground station or an Earth station, definitely that transmitter has this components in them, equipment, and sometimes it might overheat, and it will overheat. So that increase in temperature generates this randomly moving electrons in the conductor, which in turn generates thermal noise. So it's present in all electronic devices and is limited by thermal energy. So in turn, this degrades the signal quality. So example of how this would sound like is now. So it's just that toning sound. It's sometimes very low, a particular frequency. So in this case, you can use a filter to remove this particular type of noise, right? So another type of noise is the Doppler noise. So this, I'm sure from the previous presentation or previous presentation, you've gotten an idea of what Doppler effect and what causes Doppler effect and what Doppler effect is. So in turn, Doppler effect can cause Doppler noise. So it's caused by that relative motions between the transmitter and the receiver. In the case of a satellite transmitter and your ground station, either mobile or stationary. So that relative motion, because it's definitely going to be moving every single time, there's going to be Doppler noise. So it results in frequency shifts of the received signal. It varies with speed and direction of the motion and can be a significant source of interference in communication systems, and in this case, your transmitter and your receiver. So it's very important to know this, and you should know that there will be Doppler noise in your signal, because every satellite, the satellite you're going to be collecting your data from, is moving at a very high speed, and that short time that you have to get your required data from, that motion, that shift, frequency shift, will cause a Doppler noise. And this, in turn, this is how the Doppler noise sounds like. Notice that the sound, the way it started at a lower frequency, then it began to move and continue. The frequency just started shifting into a very high pitch, high frequency there. So that's how a Doppler noise is, and there's also a way to remove such noise. So I'm moving on. I'm moving on to methods of noise removal. So there's a particular way you can remove noise with Audacity. So we're going to use Audacity. So from everything you've learned so far, what you can do with Audacity, you just pick a few of that and implement it on noise for noise removal. Right? So it's very easy. I'm going to show you a few demonstrations, and you'll be equipped with everything you need to know to go ahead with your own noise removal and a successful data collection from your satellite signal. So let's hop into Audacity and I show you how to do that. Okay, now moving on to the methods of noise removal. Yeah, so you just go back to your Audacity, then you're going to implement everything you've learned so far: how to amplify, how to cut, trim, copy, paste, how to filter. You're just using one particular method to reduce or remove noise in an audio signal. So right now, from the interface, you have to first of all import your audio file. Right, so you go to Files, you go to Import, you go to Audio. Mind you, all your audio signal or audio or recorded audio should be in MP3 or in a format that can work with Audacity. So I'll recommend MP3 or WAV. Right, so right now my signal is here, signal with noise. So I'm going to select that and open. Okay, so now you have your imported audio, and now you have to remove the noise. If you listen to it right now, let me just play it back. You can tell there's noise in this signal, in this audio signal right now. So right now we want to remove, so your possible best to remove all noise, to do our possible best to remove all noise. So the easy step right now is that Audacity has this feature where you can remove noise. So the method would be, you listen through the audio, you listen to where you can hear noise and only noise. And I'm here, when you play it, you can tell that it's just noise that's here. So right now, you select that part, right? And these big notations here are the data you're trying to get, right? This doesn't have to do with the frequency, it's just the noise and the audio you're trying to get, right? So you've selected that. Now you go to Effect and go down to Noise Removal and Repair. So you're going to click Noise Reduction. Now in the first step it says get noise profile. Get a noise profile. Now you, after selecting, which you have, you click get noise profile. So it will take this selected part, this highlighted part, as the noise. So it will run it as the noise, and then when you highlight everything, so the next step is to highlight the entire audio. After doing that, you go back to Effects, you go to Noise Removal, Noise Reduction, and you go to step 2, which is the noise reduction. Now this is the intensity at which you want to reduce the noise entirely. So let's just leave the preset and click OK. So now it has done a full cleanse, we should call it cleanse, full removal or reduction of the noise in the entire audio. Now it's, as you can observe, it's a very small volume right now. When you play it back, you might not hear it entirely, but you can still hear the message, and you can still hear a bit of the noise. So instead of going back, you can highlight again. Since it's so low, you now go to effect, volume. Now we're going to amplify the volume because we can't hear it that well. Now amplify and click apply. Now compared to the last audio, play this particular part back. You can tell that there's still noise, but maybe it's not as intense as it was originally. So you still just have to repeat the process. So now you just highlight this, right? Go to effect, then you go down to noise removal and then noise reduction, then click get noise profile. After you do that, then you select everything, you highlight everything, right? Pressing Ctrl A, it highlights the entire audio signal. Then go back to effect, noise removal and repair, noise reduction, and then you go to step 2, and then you see that it's still there, the same setting. Just press OK, and it does the reduction for you. Now if you listen through, you'll probably just hear the signal itself clearer with less noise. So you can continue repeating this step till all noise is gone, or you just have to manage, right? Remember that after everything, as it reduces in size, you just have to amplify the volume, amplify the signal to get a better volume or clearer volume. So let me repeat that. You Control A, go to effect, volume and compression, then amplify. Using the preset settings, amplify it, and then you can play back to listen. If it's audible enough, then you can work with that, right? If it's not, you just repeat Control A, effect, volume and compression, amplify, and then you can go apply again. But right now it's perfect. With all noise to its minimum, you can get your audio alone, standalone. Now be mindful that when you're working on the Audacity, once you're done, you save, right? To save that, you press Ctrl S, or you go to File, Save Project. Now saving the project, right, is saving the project as an Audacity file. Right now you can save this, it's okay, but to get the audio out so you can work with it on CW or SSTV or whatever decoding software you have to use it on, you have to export this as an audio file as well. You've already done all the analysis and the modification you're doing with the audio, this audio signal, and you want to export it right now. So to do that, you go to File. That's after you've saved your work, after you're done and you're sure, you go to File, Export as MP3, WAV, or this. So right now you export as MP3 because it works on all mobile devices and systems, and then you save it as whatever name. I'm going to say without noise here, so, and save. Right, so once that is done, you can go check your file explorer. Sat pass clean. So this is the audio we have to decode. Nice. Now we'll go and get our CW decoder and run that real quick. To go ahead with this, make sure it's already picking my voice, but make sure you have your mic set operating on your system. If you want to use this process, make sure you have your mic working on your system, because as it's playing from this VLC application, as the audio is playing, this will be picking it. But right now it's picking my voice, but my voice is in Morse code, of course. So we'll play this. And the first thing you should check when you want to pick, decode any signal is to make sure that the system you are playing the audio from is playing it out of a speaker or the system speaker, and the mic is your mic is working, your system mic is working, or whatever external mic you're using is operating properly. Then you go to options here in CW decoder, you go to input and make sure that you've selected mic. That's the only way it will record through the mic, and that's when you can play your audio and it to decode. Simple as that. Now, to make this as effective as possible, make sure you are in a quiet room or quiet place so that no other kind of sound can interfere with what is going to be played, like with the audio being played. So it can effectively get your correct data out. So there won't be any errors. To avoid errors, make sure you're in a quiet room or place, and put the audio on loop. So now we're going to play that as loud as possible. Okay, so as you have observed that this is picking some letters which you can interpret later on, or yes, you have to read the message. That is the information being passed from the satellite through this audio signal. So as you can see, it did pretty well to say African Step Sat, and that's the name of the project. So moving on, basically, so I've showed you how to CW decoder is very easy to use, as you can see. And now, what are you to expect from the decoded signal in the instance that you have done all this? What are you to expect? You have claimed the data, you have done your signal processing with Audacity, and you have decoded it with CW decoder. So what are you to expect from the data received? You're to expect a battery information, your camera status, the camera, that is the satellite camera status, the satellite battery information, the satellite temperature status. That will all be forwarded through that means, and the altitude of the satellite as well. So first, it comes in this order: your homekeeping data as the name of your institution, the name of the institution, and the name of the project, which is the African STEM Sat, the battery information, the camera status, whether it is cam on or off, battery to show the values there, the temperature to show the degrees, the temperature in degrees, and the altitude to give you the value of the altitude. So that's what you have to expect. So when you do this, you can continue, you can get your data and a successful experiment. Well done. So that's it from me. I hope this was helpful. If you have any further questions, please refer to the group page created and ask your questions. We'll be glad to help you out. And with that, goodbye.
And in this video, I'll show you how to decode SSTV on your PC. Okay, so there are 5 things you need to know before you can decode SSTV on your PC. The first is what SSTV is. You need to know what SSTV is. You need to know how it's received. You need to know what it sounds like. You need to know how to install the software and how to use the software. So, SSTV stands for Slow Scan Television. It is a way of sending and receiving still images in the form of special sound waves. This is how most amateur satellites transmit their pictures. So you will receive this special sound with your antenna and the handheld radio or software-defined radio when you are tracking an amateur satellite. This audio will come with noise, either a little noise or a lot of noise, depending on how well your antenna is pointed. Also depends on your gain and how good the satellite path is. So this is what it sounds like. So in the video, I'm going to show you how to install two softwares that will be sent to you, RxSSTV and MMSSTV, and I'll show you how to decode with them. So let's get into it. Okay, so first of all, I'm going to show you how to install RxSSTV. So I'll go to my file explorer. So here, this is the setup file for RxSSTV. So I'll right click and run as administrator. Click next. Next. You can create a desktop icon if you want, but I don't want that. Click install. So launch RxSSTV. Yeah, so this is what the app looks like. Yeah, you can't really bring it to full screen. So these here are the various modes of transmitting and receiving SSTV. So this is Robot 36, Martin 1, Martin 2, Scotty 1. And this app has the ability to automatically detect which mode was used to encode the SSTV that you're receiving. So I'm going to show you an example of how this works, and I will use a sample picture to show you what this looks like. Okay, so this is the picture that we're going to receive for the example, this one. Okay, so now I'm going to load up the WAV file for the picture that I showed you. So I'll go to my file explorer. So this is the WAV file that the picture is encoded into the SSTV. So I'll play it. You can save it to your phone and then play it for your laptop to be able to decode. So I'm going to play it now. Okay, so that was the recording for the picture, and it's used you received the encoding in Martin 1. The SSTV received was encoded in Martin 1, so the app automatically detected it. So now we're going to move on to the second app. So we're going to install the second app now. That is the MMSSTV. So I'll go to File Explorer. This is the installation file for the MMSSTV. You right click and run as administrator. Then the installation wizard will pop up. Then click next. Accept the agreement. Next. Next. Install. Next. Finish. So here you can put your name or the name of your school. Okay, the difference between this app and the last one is that this one has more modes for detection than the other one. So right now it's in automatic. So I'm going to transmit the same image again with this one. Okay, so if you want to save the image that you just decoded, you can come here, right click, you click copy, then you come here, right click here, then you click paste. So now that is here, you can right click again and save to file. So now the image is saved. So thanks for watching. Hope that was helpful, and goodbye.
Hi, my name is Linus Deborah, a computer engineering student of All Nations University. So, I'll be taking you through how to go about your work and all you need to know about the computation process, which involves how to find the assignment, how to access software resources, how to submit your work, and how to come up for the next stage. Now, from this tutorial video, you go to the description and click on More. Then you'll be presented with all the links for the resources and where to submit your assignments for the Justify stage. As you can see, each link has been created such that you can access the assignment you have to do. That is the work to be done. As such, it should be the first thing you open. And there's a link you can use to submit your work upon completion. And also a link is available to grant you access to software resources you will use to work with. I'll take you through a quick demo on how to access the software resources as well as where and how to submit your assignment. To access the software resources, you click on the link attached and you'll be directed here as shown on the screen. And submission of assignment, you click on the link attached and you'll be directed to the page where you would find folders for the different stages. That is the Justify stage, the preliminary stage, and the main stage respectively. Then you click on the Justify stage folder and here you find your country folder, and if you don't, you can go ahead to create one as shown. Now inside your country folder, you create another folder for your school, within which you will create files for your assignments as well as working pictures and videos. An important point to note: for those in the science category, you are required to take screenshots and videos of your work, as well as pictures of yourself and your team as you're working. And those in the arts category, for the preliminary stage, you are required to send in pictures and videos of your work progress. That is, when you're at 25%, 50%, 75%, and 100% done with your work. And this could be taken at different angles as desired. Now, the pictures and videos taken are to be uploaded to the working pictures and videos folder with the link provided.